C'est à toi, vas-y.
Bonjour à tout le monde. Je m'appelle Jacques-Louis, je suis directeur de recherche dans l'Institut privé en santé publique à Lyon. Je suis aussi visiting professor au département de mathématiques et statistiques de l'Université de Strathclyde à Glasgow, en Écosse, au Royaume-Uni. Et je suis directeur de recherche en biomathématiques. Je suis un biomathématicien et je travaille beaucoup sur le domaine des maladies infectieuses, évidemment, et surtout sur l'épidémiologie comportementale des maladies infectieuses, et aussi sur la modélisation du cancer, niveau cellulaire et niveau macroscopique, surtout interaction entre cancer et système immunitaire, angiogenèse, etc., etc. Et donc, je suis un mathématicien appliqué, j'aime beaucoup les applications, mais aussi la théorie, donc je cherche de faire un peu tout. Je m'excuse, mais mon talk sera en anglais parce que les français littéraires, j'aime beaucoup et je suis bien à l'aise, mais avec le français scientifique, surtout des épidémies, je connais un peu moins. Mais la même chose pour l'italien scientifique, je suis désormais un peu mal à l'aise aussi en italien scientifique, donc je m'excuse. Alors, on commence, je fais share screen. Voila. So, this talk is the summary of various ongoing, mainly. Ciao, Dirk. Research I am doing in collaboration with and of various current and past co-authors, with like Piero Manfredi of Pisa University, Bruno Bonomo of Napoli University, Vitaly Volpert de l'Université de Lyon et de Lyon, Malay Banerjee de l'Institut indien de technologie à Campur, Antonella Lupica de l'Université de Messina en Italie, Rossella Della Marca de l'Université de Parma, et tous les deux très brillants étudiants de doctorat, Ernesto Salinelli, Alessio Carrozzo-Magli et des autres collègues. Voilà. Oh. Très bien. So, nowadays is common knowledge the famous SIR model. And this is the SIR model with the compulsory vaccination as a classical model of epidemiology, when the mortality rate can be neglected, which is very appropriate during the epidemics. During the epidemics, mu is 0. If it's not 0, it represents, for example, a classical model with vaccination of babies. P is the vaccination rate. Okay. So there is some classical results. For example, the famous May-Anderson threshold. That is, if the vaccination rate is bigger than this threshold, the vaccination campaign can eradicate the disease from the target population. Otherwise, the disease remains endemic and so on. But this kind of model was very good in the past when there was a near total adherence to vaccination, and many vaccinations were mandatory. But starting from 19, this was not more so good because of a series of phenomena I will shortly introduce. But the basic fact is that the basic criticism one can do of classical mathematical epidemiology, model SIR or more complex model, is they are basically inspired to chemistry. Humans are approximated as molecules in a chemical reaction in a tank, eventually well stirred if you use ODE, otherwise if you use PDE is not well stirred. Then you can have patterning, etc. It's not a coincidence that the three fathers of mathematical epidemiology, Kermack, McKendrick, and Ronald Ross, two were medical doctors, and one was professor of physical chemistry. Voila. So basically, underlying the SIR model, there is a statistical physics of epidemics. that is, the number of infection per time is abstracted on the number of collision, that is, human beings susceptible, that is healthy and infectious, are abstracted as molecule that encounters can or cannot have a reaction with a rate beta, which is the famous contact rate. So it's safe to say that SIR model is a particle-based model. But, however, currently the two pillars of prevention and containment of epidemics are pharmacological steps, such as vaccination and antiviral drugs, and non-pharmacological steps that we know very well now during the pandemics, that is decreasing the behavioral risk by implementing social distancing, both spontaneous and forced by the government. Both these steps depend on human behavior. And this is the missing part of classical epidemiology of infectious disease. For example, for vaccination, we have a lot of new phenomena. Historically, there has been small, not so small groups of traditional anti-vaccinator, people against vaccine, because for superstition reason, these are three from 19th and 18th century. The central one is Jenner, that inoculates its vaccine, and right part are people inoculated, they're transforming in cows and other animals. Yes, you know. But now there is a much more dangerous phenomenon that we call it pseudo-rational objection / hesitancy to vaccination, prova, which is paradoxically typical of rich and learned people. And there is also some experimental evidence of this. Because the underlying reasoning on the objection, which is becoming massive for some vaccine like poliomyelitis and measles and mumps and rubella, is that parents say, okay, polio is serious. However, there are very few cases in my country. Why should I vaccinate my children, exposing them to vaccine side effect? And some people go beyond. So come on, we must train our immune system. Getting measles is not so bad. My grandmother used it to bring the children to the cousin that had measles, etc., etc., etc. Okay. This, of course, is a fallacious reasoning, because the reason why, for example, in France there is no poliomyelitis is because there is huge percentage of children vaccinated against poliomyelitis. But if you start a decline of the vaccine, the poliomyelitis potentially can be reintroduced. And this is what I've been seeing, for example, for the measles vaccination, with, for example, the noises of association with autism, including a retracted Lancet paper. Now there is a second retracted Lancet paper. Every 20 years they make some publish some problematic papers. The fact is that this pseudo-rational objection to vaccination that overstate the weight of remote vaccine side effect risk with respect of the very important risk of vaccination is a phenomenon that includes a larger social phenomenon, which has been called by Ragnar Löfstedt, a sociologist from northern countries, the post-trust society. Now people say, X is working on vaccine because it's paid by big pharma. Government push in favor of vaccine. Big pharma is behind. They want we get diseases, etc., etc., etc. And this synergizes with another phenomenon, which is different, but of course has overlaps interaction, the post-truth society, that is the diffusion of fake news. Voila. Yes, I forgot. I have the slide. So this is let's say the graph of the use of post-truth. And you can see there is an exponential explosion because the phenomenon of fake news is huge. Well, so some margin, as we know very well, human beings are not particles, but we could say, because the approach of statistical physics remains essential, but in a different way, are active particles, and they are endowed with a psychology and behavior. The first paper that introduced the elements of behavioral epidemiology was a paper by Vincenzo Capasso and Gabriela Serio, published in 1978 in Mathematical Bioscience. The science must adapt. This is a limited sample of human beings that have very different behaviors. Okay, they are not particles, of course. Okay, so a little bit of advertisement. Due to emergence of this very, very, very important phenomenon that concerned vaccination and the impact of the change of human behavior, social distancing, which has been also observed during the Spanish flu pandemics, for example, but also historically, is that a new branch of mathematical epidemiology and more general epidemiology was born some more or less 15 years ago, the behavioral epidemiology of infectious diseases. This is a book, I think very interesting, that we edited in 2013 and was the first book ever published on this topic, which is now becoming increasingly of interest, let's say. Oh, okay. Before illustrating some qualitative models in behavioral epidemiology, I want to stress its main limitation. You see, in our book in 2003, we decided to start it, although it's a modeling book, with 3 statistical papers, because the main problem, at that age at least, was the investigation of the behavior part, because there are, now for COVID, there is many data for the epidemiology part, but for the behavior is more problematic, especially at that time in 2013 was very problematic and there was very few studies. This was basically the 3 main studies at that time. Okay, so now the scenario is improving. We are giving much more attention to data with experimental study of psychological type and sociological type, and by analysis of social network. This is, for example, a simple, let's say maybe not so simple study of the impact of contrasting political declaration communications on vaccine on Italian vaccination rates. Okay, so this is a very, very important point. Oh, as I mentioned, the first SIR epidemic model was the one by Capasso and Serio in 1978. Basically, Capasso and Serio modeled the contract rate in the Kermack-McKendrick epidemic model, that is mu equal to 0, as a phenomenological decreasing function of the prevalence of disease. You can also use the incidence, of course. And the model is very important, but of course, it assumes that people decides basing on the current information on the current prevalence. We extended this model in 2008, and the extension is not because we added also the endemic terms, but the key point here is that people take decisions not based on the disease, but on the information, biased or more hopefully not biased, you have on the disease, and also on your memory of what happened in days, weeks, maybe in some cases years before. That is, if during the middle of the pandemics, a day for a statistical fluctuation, the incidence of the disease, for example, was smaller than the day before, not for this reason people stopped the social distancing. There is a little bit more or less long memory. So we defined this variable that we had defined for similar purpose for vaccination model, M, which we call it information index, which can be, in the most simple case, a function of the current state variables of system. For example, the incidence or the prevalence. Okay. But more likely is a non-local in time function that is taking into account of the memory of past data. And the memory is fading. For example, a model is the exponentially fading memory of the kernel. Another plausible model is Erlang or extended Erlangian model, where the nucleus at zero is zero. And this is very good because you are modeling in this way the fact that in a lot of cases you have no or very scarce, very few information of the current state of the disease. Okay, and well, we made mathematical studies by showing the global stable the local asymptotic stability of the endemic equilibrium. Then with Cruz versus De Leon, we showed that the endemic equilibrium is also globally asymptotically stable. And we showed that if the kernel, as I mentioned, is now null at zero, you can have Hopf bifurcation with onset of a periodic limit six cycle. Okay, and of course, what is the topic of the day? Is the contact rate of COVID seasonal or not? Well, this wasn't, of course, not on COVID, but a simple SIR model. But if in this scenario of an endemic SIR model with behavior, we take into account the seasonality, we found for some values of the parameters chaotic behavior, that is erratic pseudo-random time series. Okay. The model we presented was simple and quite explicit. Poletti, Ayel, Merler, and Pugliese in 2008 had also proposed a model of behavioral changes of the contact rate based on an economic imitation games, where the model is very simple and can be made also more complex. But basically, suppose there is two groups of people that continues to have a normal behavior and people that becomes more prudent. So we have these two fractions, a fraction of people that have a low number of contacts, let's say, thanks to social distancing, a number that have a larger number of contacts, and they are mutually exclusive. This is a huge simplification. You can make an integral differential version of that model that I'm building since some years, we can say. Okay, we proposed now, this is a work which we are finalizing, a new model where you have both the imitation games, that is people exchange information and change, but also the media influence, which is unidirectional. For example, the social networks influencer, not necessarily propagator of fake news, are basically unidirectional influencer. Whereas if you freely discuss in a forum, this is an example of real limitation. Okay. And we add then public health efforts to reduce the behavioral risk at risk. Okay. So we have X, denoting with XL, the fraction of people that adopting behaviors with low risk, and each H, fraction of people adopting normal behavior, which are mutually exclusive. You can derive a formula for the contact rate. Okay, and you have basically this model. Okay, of course, this model is incomplete because you have a function that expresses the contact rate in function of the fraction of people adopting low-risk behaviors, but you don't have the model of the XL, basic. So, a first simple model that does not include the social network, influencer, television, and press, but included the action of the government, is this one. This in an imitation game, not in an economic version, but in this original version, because the process imitation can be seen as a double mutual process of contagion of ideas. People discuss and can switch from one strategy into another, and from the strategy L to the strategy H. Plus, the last two terms are the terms of the action, the effects of the action of the government that can induce the switch from the high-risk behavior to the low-risk behavior. Taking account that the two are mutually exclusive, you have a very simple ordinary differential equation, where the first part is the classical imitation dynamics of the evolutionary game theory. Plus, there is a control term. Okay, this, let's say, forces of infection, it depends on the information, and of course the C, that is the rate of switching from the strategy high risk to low risk, is an increasing function of the information of disease. Because if there is, there is a lot of cases, you more easily switch from high risk to low risk. Whereas D is the contrary. If you know that there is not so many people diseased, roughly speaking, it's more probable that you can switch from high risk to low risk. Ah, comment il n'y a plus l'épidémie, on va fêter tout ensemble, jouer au foot, more or less. Voilà. So we obtained some interesting mathematical results, in the sense there is a threshold that induces all the population to adopt a low risk. And of course, in the practice, this threshold, I think, is not reachable, but mathematically, and maybe in some case, is feasible. Okay. Then the eradication of the disease is possible, provided that you use a specific kind of control proportional to this. Okay, various other, but what is missing in this model is, as I mentioned, the fact that it is not included what is the real, let's say, the real phenomenon underlying the switching of strategy. That is the inclusion of media-driven changes that are unidirectional. That is, influences the sources that want to influence, not influence, sorry, but are not influenced. Influencer, or the all news TV channel, the print and then the online press, etc., etc. So, the first two terms, models, this kind, the fact that people receive information and switch from high risk, let's say, behaviors to low risk, and vice versa. And this is corresponded to the ordinary differential equation we have in the second line. Okay. Oh. And the first interesting fact is that, very simple, but if you assume that there is this effect of the people that are influencer but cannot be influenced, this the very theoretical result of having with appropriate state pressure 100% adherence cannot be reached. Voila. And now let's, of course, we can do a very nice analysis and the control and the optimal control of the full model, but it's very interesting to examine the and also more easy for a talk model where what matters are only the unidirectional information. So people are a little bit passive, the receivers, and then decide. So the model reduced to this, of course, remains present the pressure of the state. Oh, of course, the lockdown can be seen as making gamma of T very large. And I also specify that you can make more realistic the model to take into account that some people are forced to have high risk behaviors, policemen, medical doctors, etc., etc. Okay, so there is an eradication threshold also in this case, but another sub-case very interesting is this. We have to know which are the dynamics, the time scale of the dynamics of the changes of opinion or public opinion. Well, there is a lot of evidence that, especially in case of very serious disease, the people switch very easily. That is, there is a strategy, there is a volatile opinion. In this case, if you apply a quasi-steady state, you obtain a quasi-steady state formula approximated. And note that in the case of where the action of the government is constant, you reobtain the model I published in 2008 with Piero Manfredi. And in the special case where the information index is equal to the prevalence, you obtain also the Capasso-Serio model. This is quite interesting. Of course, you can have a theoretic control, because if this is value of the government action is bigger than this formula, you have the eradication, of course. This was for the endemic case. But let's now specialize to what's very important now that we have a worldwide pandemics ongoing. Okay. You have an epidemic scenario with social, no more an endemic. So all is important is transitory, and since there is not many theoretical results on transitory, unfortunately or fortunately, depends of the taste, you have to resort unequally to simulation. But in any case, if we consider the model with the information and the endemic case, and you include the memory and the mild constant control, and apply to SIR model, similar can be obtained with result with much more complex models such as those of COVID. Well, if you have this behavioral reaction, but not enough action of the state, this scenario suggested by the model is that you can have multiple epidemic waves. I repeat, in case of the government have also a mild action, so let's say intervene a little bit, maybe only suggesting to old people to stay home, etc., etc. The model predict multiple waves. Of course, there is a switch to be made. The figure at right corresponds to a basic reproduction number of 2. The figure at left corresponds to a basic reproduction number 15. What is a little bit interesting is that this maintains also with small population. This was a deterministic model. But if you consider a stochastic model, that is, you study the same problem for small population, also in this case, you can have multiple waves, as you can see from this simple picture. What are the qualitative indications from these models? Is that, yes?
What are the different colors in the previous, in the 2 previous slides, the black, the red, and the...
Yes, this depends on the reactivity of the population. That is, in black, if people start to be scared, let's say, with a large prevalence, information the prevalence, the red is intermediate, and the blue means very reactive. That is also with a small number of cases, people say are scared and prefer to implement social distancing. Okay, and the same also for this stochastic picture. Sorry, I forgot to say. Of course, when people are not so scared, relatively, you have epidemic peaks of larger prevalence, although much smaller than in case you don't adopt social distancing, of course. And if you are a lot scared and this is very roughly speaking, of course, and you start adopt energetic social distancing with very small number of infectious, in reality it's not exactly this because they take account of delays, memory, information. You can see that also in the blue case, where the epidemics is pretty well controlled, yes, we can say this, you have multiple peaks. The model the model predicts also in this case that is teeny population, small population, and a lot of reactivity. We had expected for this case to have no second peak. No, you have multiple peaks also in this case. So this is something to think about. So what are the qualitative indications of this simulation? That suppose also that you also implemented a full lockdown. That is, the epidemic curves are much better. After, if you live exclusively to the population, the implementation of social distancing of population, have other epidemic waves. But that is what you have to do is to implement policies, not mandatory because the lockdown is a mandatory policy, but pressure with various methods, including stimulating the general practitioners to favor prudent behaviors. That is, the lockdown is no more there, but you have to work to favor to media, etc. What is a little bit doing now all the European states at least. But the second indication is not for public health policy, it's for modelers. That is in reality behavioral epidemiology must involve also the behavior of government. That is no more important only to model and understand the process underlying social distancing, vaccine acceptance, etc., but also how to model the process of decision making at governmental scale. Oh, let's apply this concept to COVID-19. Oh, this is a very recent preprint. Corresponding author is a very brilliant PhD student, very impressive, from economics department of Bologna University, and then Piero Manfredi, and I also contributed. Deteriorated COVID control due to delayed lockdown. This delayed lockdown is a result from strategic interaction between government, opposition, and the lobbies. This is missing in the title, so maybe in the paper which are going to submit will include also lobbies. So, because you see in many European countries, the lockdown was quite delayed. For example, Belgium. In Belgium, they started the lockdown when we reached near 1,500 confirmed cases, which corresponds more or less, taking into account the population, the date of lockdown for France. Italy was even more delayed, and so on. Okay. Germany is a little bit particular because they, in any case, had a very effective practice of contact tracing. Okay, so also Spain, they started the lockdown a little bit late, UK, we know very well what was the main trigger to go into lockdown. So there is this European problem, and let us not mention the USA. Okay, so this model, of course, to understand to model the political decision, also in this case, the game theory is very appropriate. So we have government, but if you speak of game theory, we have to speak of players. Which are the players? The government, the opposition, not when it exists, and lobbies, for example, industrial lobbies that can have interest to delay the lockdown. This is what happened in many countries. Okay, and who says game theory also says payoff matrix. How is the payoff matrix of the government, let's say, game? Let's call it. Of course, is not a constant payoff matrix, but a very complex, because here we have triply and so on, matrix that depends of the incidence and on the mortality during the pandemics. Is very, very, very complex. Oh, and to do this, of course, it's a quite theoretical model. Unfortunately, I'm very theoretical, but I like also data. But in any case, for the moment, we're based on a very simple ordinary differential model of the COVID-19. Okay, and this is the prediction or qualitative prediction of this model. What is the delay? Which is the impact of delayed versus almost non-delayed lockdown? Because, well, this game is very complex, but there is some case where the government is very, as a real unique priority, citizens and also opposition. They agree. In this case, they are able to overcome the pressure of lobbies. So this is the case of right. In this case, the epidemics, of course, there is a little bit of delay. It's not excellently controlled, but reasonable. Okay. The left simulation refers to the case where government is more sensible to the lobbies are more effective, the opposition is a little bit more confused. And as you can see, although the curve of new infection, new hospitalization, and new deaths, and the cumulative deaths, that is the insert picture, are qualitatively similar, okay, then the scale are very different, because you reach, for example, a peak of 7,000 new infection, for example, etc., etc. So, what are the suggestions from this model?
Alberto,
the lobbies, yes?
Yes, I don't understand the X variable is time is expressed in years?
No, it's not years, in days, No. Thank you very much. I will write immediately to correspond authors. No, thank you very much. Oh my God. This happens when you cut and paste from MATLAB code for other simulations. Okay, no, thank you very much. So this is an ideal case where it takes centuries to have the epidemic peak. Okay. So the model, what suggests this model? This model suggests that the lobbies, the action of lobbies are deleterious. The main cause together where it occurs, luckily occurred not everywhere. Italy, unfortunately, occurred, not in France, let's say, and also not in UK, where, of course, the political opposition is not in synchrony with the government, and both or the government is not is more in synchrony with the lobbies and or moderately with the lobbies and not with citizens, the lobbies' action are deleterious. In all cases, are deleterious. Okay. The early lockdown is possible only if government is fully, is fully responsible with respect to citizens. And the lockdown can be adopted even earlier if also position, let's say, is in resonance, let's say, with the government. And it's interesting that it's possible a vicious circle. That is, suppose the lobby is very powerful. You have very delayed lockdown. So what happens? In this case, a longer lockdown is needed, but more or less in the middle of this long lockdown, there is large economic losses, and there is huge pressure on lockdown, etc., etc., etc. So theoretically, it's possible to do this. Well, an important caveat. And the space, that is the model I showed, are simple model based on ordinary differential equation. But this does not mean that the space is not important. And in particularly specific actions related of social distancing, for example, or vaccination related to spatial phenomena. And I work on this in collaboration with the Malain Banerjee and Vitaly Volpert, of course, my friend Piero and Antonello Lupica and other people. And I recently published a paper in January of the effect of spatial social distancing. The fact that if you know there is a large concentration of infectious, avoid to go there. It's a very theoretical model, but basically say that if the disease has clusters, an appropriate social distancing can destroy patterns, both Turing patterns and also the more complex and often chaotic Turing-Hopf patterns. And also for vaccination. I did not show here the models for vaccination, but of course we started working on behavioral epidemiology to model the vaccination hesitancy. And in vaccine, you take into account also non-local information. This is also true on social distancing. And if you include this non-locality, you can have generalized traveling waves that occur, some complex phenomena, etc., etc. So unfortunately, I have no time to illustrate them now. So one limitation of behavioral epidemiology was the lack of space. The lack of space has been introduced. The major limitation was the fact that theoretical models were not based on data. Now data starts arriving. But there is another very big limitation of behavioral epidemiology models. That is the agent acts in a manner that is in some cases rational, the fear of diseases. In some cases are pseudo-rational, that is people have excessive fear of vaccine side effects, overweight the risk of vaccine side effect, but it remains a deterministic behavior, not really rational, but para-rational, let's say, and from mathematical point of view can represent it in a deterministic way. In real life, people increasingly acts in a partially irrational way. How to model irrationality? This is a complex problem. One possible solution is to model irrational components of behavior as stochastic perturbation. And so the models are based on the stochastic differential equation and, of course, stochastic partial differential equation to take into account the space. Okay. So, I don't know if the time is finished. If yes, I can go to the last slides. Otherwise, I can speak some minutes on this kind of modeling with a very simple example.
You still have.
I have some minutes more.
Yeah,
Yes.
there is some time. Yeah.
Oh, very well, very well. Okay. So we start with a very important case we very recently submitted, and the focus can seem strange. How to favor the dynamics of vaccination rates in a population where the disease is absent. It seems a little bit strange, but in reality it's very important. Again, a typical case is poliomyelitis. All world is vaccinating against poliomyelitis, but poliomyelitis currently is present in very few nations, and there is a lot of objection to vaccination to poliomyelitis. Oh. So we denote with X the fraction of population in favor to vaccine, which will correspond, assuming that parents have more or less the same behaviors of general population, to the rate of vaccination newborns. This is very direct. Well, the problem here is to model the reaction of vaccine side effect. Well, how to model this? We model it in a very simple way that can be a little bit more sophisticated. We assume that this number, or the information on this number in more complex model, is a good proxy for the vaccine side effect rate. Of course, because you do a lot of vaccine, you have a little bit more of the vaccination than they are amplified. The other state variable, in reality is a false second state variable, is the fraction that are against the vaccine and do not vaccine their babies. And of course, since there is only two strategy, A is equal 1 minus X. But is instructive from the derivation point of view to start with the complete model. So you see that you have a flux from anti-vaccinator to pro-vaccinator, and a flux from pro-vaccinator to anti-vaccinator. No, excuse me, in the second line there must be a plus sign, plus dx, sorry. And there is the government action to favor the vaccination that allows that some people change strategy from anti-vaccination to pro-vaccination. Of course, the constant rate C is an increasing function of the information, or in this case was the simple case of the disease prevalence, and D, that is the rate where you change strategy from vaccinate to no vaccinate, is an increasing function of the number of vaccine side effect, that is with its proxy, which is X itself. So at the end of history, if you take into account only rational behavior and para-rational behavior, that is, if you have a deterministic model, and you assume the simplest case for D, that is a linear affine one, and the disease is not present, so C is constant, you have this very simple model, defining delta as C0 minus A0. You have this very, very straight, simple model where X tends to an equilibrium value. Okay, if there is an equilibrium percentage of fraction of vaccinated newborn, this is the ratio between delta to alpha. Of course, in the happy case where delta is bigger than alpha, the P will be equal to 1. But this is very theoretical and never occurs in the reality. In the reality, P is something in the middle. So, what is the simple assumption to model irrationality? Is that the baseline rate C0 and D0 are affected by stochastic fluctuation due to irrational behavior. And in the first approximation, we can assume that these fluctuations are due to influence of social media, etc., etc. So they are very frequent. So the noise is very fast. So we can say that the parameter delta can be modeled as perturbed by a white noise. So you can obtain a apparently simple Ito stochastic differential equation, which I wrote in the two ways, statistical physics and mathematics. Okay, so if you see the structure of this model, which of course this is a classical structure of a Ito differential equation, is that if exists some points where both the drift and the diffusion coefficient function, are 0, they are stochastic equilibria. That is, if you start from there, you remain there. But are they locally stable or not? This is more complex. So our model has not one, but two stochastic equilibria that coexist. Zero, that coexist, that exist in the same time. 0 and 1. Oh, defining a change of variable and applying Ito rules, you obtain this different equation, and whose solution is this one. And these allow the parameters, let's say, investigating the parameters, you can understand that some interesting scenario can happen. In particular, if the equilibrium value of the vaccine is smaller than 1/2, and the diffusion coefficient D is in a given interval, the model predicts that X tends to 0 almost surely. That is, this fluctuation can induce a scenario of no vaccinations. Similarly, is the equilibrium vaccination is bigger than 0.5, and it holds this, and the square of diffusion coefficients is in a given interval, that is quite meaningful. X tends to 1, that is, this fluctuation can make the system tend to 0 or to 1. And there is also a stochastic B-stability scenario. That is, if the diffusion coefficient is bigger than a threshold, we have that both the stochastic equilibrium are locally stable in stochastic sense. That is, we have a configuration of stochastic B-stability. So, if D changes for some reason, there is more large fluctuation of the noise, one can pass from 2 stochastic attractor to 1 and vice versa. So we have a scenario similar to first order phase transition, because and not noise induced transition. Noise induced transition are a qualitative phenomenon where you can have a probability density function pass from unimodality to bimodality, whereas a first order phase transition, you pass from a scenario where you have stochastic B-stability to stochastic monostability. Okay, but in that equation was missed the public health system action, and of course is beneficial. First, you can see, so there is an additional term which is the control. The first positive effect is very important. It is you remember the X equals 0, there is no vaccination, what a stochastic equilibrium. In this framework is no more a stochastic equilibrium. Oh, and of course, if gamma is bigger than a threshold, in case of gamma is periodic, is bigger, if its average is bigger than a threshold, you can induce a scenario where all people vaccinate. Of course, unfortunately, this threshold also in this case will be very large. Oh, these are theoretical models that can give some suggestion to public health and can be improved by taking into account quantitative data. They are all built based on qualitative epidemiological knowledge. They're not something we taught in the morning. But in the reality, the implementing this politics is much more difficult because we live in these two we are experiencing these two phenomena. Our society is both a post-trust society with post-trust political parties also. A very impressive fact is that in the most recent regional election in Italy, in Emilia-Romagna region of Bologna, which was a traditionally left region, let's say, the anti-vaccinator party had 0.9% of votes. You say very well, very small percentage. Apparently 0.9 is not so small. But the most impressive fact is that the Communist Party had the 0.6. That is, a party based totally on fake news and the post-trust was able to have more vote than a party that is structural in the territory. Not very able to get votes, but it's very impressive, this. And we have also living, and this is also related to anti-vax power, in the post, as mentioned, in the post-trust society. And there is evidently a synergy. And it's a very big challenge for modeling and with very interesting mathematical perspective, because there is a lot of non-locality phenomena, for example, because you don't take into account for your decision all your local information, but also in the region around you, or even in the national at worldwide scale, or a mix of these three components. And there is the problem of age structure, which is very important for COVID. And the network-based modeling, and of course, a very important topic of application where I'm working intensively. I had no time to explain today, is the application of optimal control theory. That is applied to, for example, how to design this politic gamma T, let's say. And also some numerical implication, because the algorithm for optimal control, the algorithm that use the Pontryagin theorem, do not work very well, and the heuristic global optimization algorithm works very well, but it's a little bit a pity, because it means that you don't take into account the Pontryagin theory, which is wonderful. And so there is a lot of problem in all fields of mathematics, of dynamical system, let's say, that can be usefully applied in behavioral epidemiology. Oh, so thank you very, very much to Yvonne, to Pierre-Alexandre Bliman, and all people involved in this wonderful series of seminars for inviting me, and that's all, folks. Voilà.
Okay, thank you, Alberto. That was a very nice and informative talk on the different subjects that we had classically. So there is already one hand which is rising. Dirk.
First of all, hello, Alberto. Nice to see you again after many years.
Yes. I'm searching to reappear in the screen, but I don't know. Maybe stop video and start the video. No. Oh, it's not important. Okay.
Okay, you are here actually. You are on the screen. Just some question concerning the noise. In the end, you went to this subject. I think it's important. For example, if you look at if you think of confinement, then the cases of new infection and so on, they become more and more rare. So probably it is fundamental to take into account stochasticity in this case. And actually I have three items. The first one is a question to you. At some point you did include noise already before the last part. Yeah, that was where you considered where you saw fluctuations in case where the people were either cautious, very cautious, or even or not so cautious. Then you had cycles with at some point stochasticity. How did you represent the noise here?
In that case, the noise is intrinsic noise. That is, the model was simulated with an extension of the Gillespie algorithm. Why an escape?
Okay. So that means that you represented more or less the different state transitions as chemical reactions, and then you formulated the master equation. Is this what you did?
Yes, exactly. And but with a complication, because in this case, the reasoning and using the jargon of computational chemistry, the propensity rates are time depending. So you have to use a variation of the Gillespie algorithm that was introduced first for the deterministic case, that is not for the deterministic case, was introduced first by Gabriel Turinesi, Alfonsi, and other people from Paris. There is a very interesting paper in the early 2000s. And then I also extended with my friend Giulio Caravagna and Giancarlo Mauri to take also into account extrinsic noise. So you can also add extrinsic noise to model this phenomenon.
So okay, Alberto, just a question. Can I contact you somewhere, because we are setting up something as well, and I would like to discuss this with you. Would this be okay? Before
Yes.
Okay.
It will be a pleasure.
Then the second point actually that I have is the second question is, in the end you use stochastic differential equation, but
yes.
in most cases stochastic differential equation, then the noise term, if you ignore for a moment the amplitude, is that well, even if you have multiplicative noise, it emerges somehow of it's the Gaussian then you usually use the Gaussian approximation, right? So you are not in for most reactions you cannot the exact the ODE with the noise term, the way you've shown it, is not the exact continuum case of your master equation noise.
Yes, but
so doesn't this matter?
No. There is also a very important point, is that in, let's say, real noise, in reality is bounded and colored.
Yeah.
So I have also a version with bounded noise, etc., etc. And of course, it's a rough approximation of what happens for X small. In the reality, the extinction or the two fixation, let's say, to 0 to 1, can occur much before, and you can use, for example, a WKB approximation, like the one that use Baruch Merson and Michel Assaf in their interesting studies on the population dynamics. So this is, of course, the underlying hypothesis is that the population is very large. But of course, this is, as all the result for stochastic differential equation, is approximated and a little bit very rough when the number becomes small, because in reality the probability of extinction is larger. One should use some sort of hybrid model, in the sense that first you can use directly the Gillespie algorithm, but it's not so feasible when the population is very large. Otherwise, you can use, which has been very used in literature, some approach where you let's say switch to the Gillespie algorithm when the number of the people is smaller than a threshold. But in any case, it is interesting that if we want to use in that model the real model, that is a model where you have both noises, bounded noise, and the discrete population, it has been, one must use an algorithm that I introduced in system biology some years ago in +1, 2015, I think. That is exactly for the simulation of system where we have both intrinsic noise, that is a birth and death process, and the propensity rates are perturbed by bounded stochastic fluctuations. So I perfectly agree with you. I take the most simple way because the time for the talk was...
My last very short point, I'm sorry, that just this.
No, it's very interesting as usual.
So, I mean, it's exactly, you mentioned this already. I mean, if you get to really small numbers, and if you would even spatially resolve, then the chance that you get to so small numbers that in most cases you have extinction, for example, and in a few cases maybe explosion, makes reliable prediction almost impossible, right? So how do you deal with this?
No, but of course, this is a qualitative model that simply warns, especially for the case of x tending to 0, warnings that this kind of fluctuation can induce period of very low vaccination. Because indeed, if you use more realistic noises, you can see also, for example, bounded noise, the distribution are not too, for example, in the coexistence case, are not, of course, to Dirac's delta, but a bimodal distribution, let's say. Of course, this is a very simple model. The most appropriate model would be an individual-based model, where you take into account more precisely what happens, and eventually you can pass from the individual-based to the field, when it's possible. Fortunately, it's not every time possible. So absolutely, for example, an approach based on individual-based model would be fundamental. Absolutely, I believe, especially for COVID, and it's not a coincidence that the most cited paper on COVID, which is the paper by Ferguson and co-worker, is individual-based model. If you yes, okay, if you read the famous paper by Ferguson that pushed Boris Johnson to the lockdown, is an individual-based model. So I'm greatly in favor of individual-based model. Absolutely.
Okay, great. So I'm going to, if you give me your email, then I would contact you, because we're working on something like this.
Absolutely. I will write. I know, write to Dirk.
Great, thank you.
Okay. Is there further questions? Raise your hand or make a sign. Yes, I have a few. Pierre-Alexandre, yes?
Yeah, hello, hello Alberto. Nice to see you. So yeah, it's a very, very nice questions that you raised. So concerning this your talk, so there may be apparently two networks of interest within to describe this phenomenon of epidemics. First, a network of infection, and then a network of influence corresponding to vaccination, but also, for example, but also corresponding to how the people respect the lockdown, how they wear or not masks, and so on, how they behave, generally speaking. Yeah. So there are two networks which a priori are, I guess, independent.
Yes. No, there is an interplay in the sense that people take the decision based on information. There is a mutual exchange in the sense that the decision, the network that concerns the decision and the behaviors is influenced by the information you have on the epidemics, and vice versa. That is, your behavior directly changes the course of the epidemics and the ability of state of control it.
Yeah. But these, well, for both these networks, you may have or not homogeneous world or not. I mean, you may have heterogeneous networks with, say, a distribution of contact rates or number of nodes.
Exactly, okay? Exactly.
Can you hear me?
For example, the model I showed on the dynamics of the contact rate is very simple to strategy.
Okay.
And basically, two strategies
Can you hear
mean
me?
2 levels of contacts, whereas the
Yeah.
reality is much more distributed.
Yeah. Okay, it seems that my network is quite weak. But so my question is, there have been works on that issue. So the interplay of two somehow heterogeneous networks, and to see what is the global behavior of the epidemics within this
Yes,
coupling.
especially for vaccination, there is a lot of works on the impact of behavior and with multiple networks, etc., etc. If you see not the advertisement, my long one, I'm only one of the co-authors, on the statistical physics of vaccination. It is treated a lot. I don't know about all the simple behavior, but I think there is something. There is something, of course.
Thank you.
Okay,
You're
thank
welcome.
you.
Merci bien.
Other questions? So I have one. I will share my screen because we don't see your screen anymore. So on this plot, I don't see why there is a delay. Why this comes so rapidly and this comes later? Do you understand why?
The reason why yes, because let's say
which was not the case here.
Yes, because the simulation here is basic representation number equal to 2. That is correspond to a stochastic version of the right. If you see, is a little bit similar. There is a delay, and then there is.
Yes, the maximum of the blue is before the maximum of the black, because at the beginning it starts exactly the same. Here it starts earlier, so the peak is before, but the start of the increase here is before this one.
Yes, this is a nonlinear effect, because in the blue case, you have to take into account that both there is a delay of information. Okay. In the blue case, you can see initially starts the epidemics. Okay. Then the reaction is very energetic. So what happens is the epidemics reach a very, very small maximum. Whereas in the other case, the epidemic starts, and due to the interplay between stochasticity and delays in the behavior, you have this interesting paradox that is the epidemics up. The peak is later, but is much, much bigger.
Yes, but also after these days, there is almost equal 0 the number of.
But not 0, because this is
but very small with respect
yes,
to
because in this case the people are much more reactive. Being much more reactive, this means that both the peak and the minimum are small, and in the blue case, after 200 days, you have also the extinction. Whereas in the red and in the black case, you don't have the extinction.
Okay. Okay, I catch it a little bit. Yes.
Pardon, I have to move.
Yeah. Hello.
Hello.
Okay.
I still don't understand it, actually. Do you understand it? Why doesn't it go up at the same, nevertheless at the same time? It's not clear to me.
Not really clear. It's the inclusion of stochasticity, if I understand well. It's inclusion of stochasticity, but I don't really see why it's why there is this effect.
It must be multiplicative noise effect, right?
No, this is due to the interplay, which is very complex, between nonlinearity, stochasticity, and temporal non-locality.
Well, there must be a delay somehow in the system.
Yes, because the information takes into account the memory of what happened in the previous days, etc., etc. So the result in this, of course, is not trivial, because here we have a lot of you have nonlinearity, you have stochasticity, and you have temporal non-locality.
Probably would have to see the equations to understand.
Yes, but so do you think this is real? So this is a nonlinear effect of the model and due to stochasticity. Okay, but
Yes.
I better understand this behavior where at the beginning every slope, every curve is similar, and then there is an action, okay, realization that makes it a different curve. Here, the beginning is not the same, which is a little strange for me.
No, but this is because the model is very different. In the first case, is deterministic.
Yeah. But
so evidently, one misses some effects. And another things. This is a very important thing is the following. This is three single realization.
So it could be that you have so you have a delay maybe that is controlled by the stochasticity. So the first you have a longer waiting time for an individual for the first event.
No, the waiting time is the same. Is a pure effect of this interplay. And in any case, these are single items of the simulation. Of course, we made also the probability density function.
Okay.
But it is in any case interesting. The fact is that for this reason also they don't start exactly. But of course, being stochastic never is. We have two instances of the stochastic process. They are never equal, and there is this kind of phenomena, etc., etc.
Yeah, but the red and the black go in the same direction. So
yes.
I was just wondering. Okay. So if there is no more question, I think we can stop. And thank you again. This was very interesting.
Merci bien.
There are the references to the papers that you proposed that we can go and further discuss. Okay.
Yes, but in reality, the majority are just submitted or in submission. So as I said before, I will work to submit and maybe send the links of the preprint. Thank you very much.
Thank you
for
again.
inviting me.